Nuclear fusion power is like creating an artificial sun. In contrast to nuclear fission power, which splits atoms into lighter elements to generate energy, nuclear fusion power utilizes the energy released when lighter elements are combined to form heavier elements, similar to how stars produce light. Nuclear fusion reactors use deuterium and tritium, heavier isotopes of hydrogen, as fuel. At extremely high temperatures, deuterium and tritium collide and fuse into a heavier helium atom, releasing a neutron as a byproduct. During this reaction, the decrease in total mass is converted into energy. At these high temperatures, the electrons of atoms become detached from the atoms, forming a plasma state where they spread out like a gas, and the atoms that lose electrons become cations. Ions carrying electric charge can be controlled using the magnetic field of a fusion device, but electrically neutral neutrons collide with the plasma-facing material, PFM, causing damage. When this chain reaction of collisions involving neutrons occurs, the regularly arranged metal atoms of the PFM dislodge from their lattice positions and become disorderly distributed, causing some portions to momentarily melt. As the temperature drops, most atoms return to their lattice positions, but some become trapped in between lattice points, becoming interstitial atoms or creating vacancies. Voids or agglomerates formed by the accumulation of such defects are the causes of performance degradation in a PFM. Researchers have analyzed this defect formation process using molecular dynamics. However, due to limited computational resources and the absence of codes capable of handling large-scale problems, they could only study systems of very limited scale, typically in the range of tens of nanometers or smaller. The microstructure of the real material comprises a polycrystalline structure consisting of grains, small crystalline fragments regularly arranged ranging from tens of nanometers to hundreds of micrometers in size, along with grain boundaries, which are boundaries between different grains. In particular, grain boundaries have a significant impact as they interact with neighboring defects. To accurately capture the influence of these grain boundaries, massive computational specimen on a micrometer scale is required. For the calculation of large-scale computational specimen, Professor Byung-Chen Lee from the Department of Mechanical Engineering at Kyunhee University and Professor Gan-wook Kang from Yonsei University, along with their research teams, utilized the Kisti's fifth supercomputer Neurion. As a result, they created a micrometer-scale system composed of 100 billion atoms and developed a computational code capable of performing molecular dynamic simulations. The research team used the computer modeling to predict collision locations and energies, then investigated how defects form as a result. First, large-scale computational specimen with a polycrystalline structure measuring around 600 nanometers to 600 nanometers to 400 nanometers in length and comprising roughly 8 billion atoms was used to replicate a structure identical in size and shape to the real thin film experimental specimen. Next, the team calculated probabilities of where neutrons collide within the specimen and with what energy during neutron irradiation. Based on this, they employed acceleration techniques that simulate multiple collision cascades simultaneously to examine how defects are formed. This analysis confirmed that grain boundaries impede the growth and progression of collision cascades, while also absorbing defects caused by the collisions. In addition, the team observed changes in the shape of the grain boundaries and the formation of known defect structures, such as defect loops during quenching process of damage cascades.
지금까지의 시뮬레이션 연구들은 대부분 이상적인 상황을 가정하여 수행하였기 때문에 그 결과가 굉장히 제한적이고 또 정량적보다는 정성적인 분석만 가능하였는데 본 연구에서는 크기, 조사량, 그리고 조사 손상 또한 실험과 1대1로 비교할 수 있게 되었습니다.
In preparation of the upcoming exascale era, a preemptive large-scale simulation infrastructure constructed using the supercomputer Neurion surpasses conventional molecular dynamics which were limited to interpreting microscopic phenomena at an atomic level. This infrastructure enables research into material properties using large-scale specimen at a micrometer scale.
본 연구에서는 K-스타 핵융합로에 대면제로 사용되고 있는 텅스텐의 원자들을 해석하는 연구로서 다결점 구조를 파악하고 이를 통해서 전자현미경 수준의 실제적인 연구가 가능하도록 한 큰 성과가 있겠습니다.
The large-scale computational simulation infrastructure is expected to play a vital role in connecting the nanoscale and microscale domains in multi-scale dynamics across diverse fields, encompassing not only neutron computational simulations, but other areas as well. Thank you.